This is Science Max, Experiments at Large. Science Max! Today, I'm maxing out the power of water. Water is very heavy. Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max, Experiments at Large. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it, though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car. You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom. Trim them down, maybe about that much. Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick 1 wheel on, put the skewer through the straw, and do the same thing on the other 3 sides. Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base. Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside. And don't forget your safety glasses. Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with 1 finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it, and kink the straw, and woohoo! Woohoo! Haha, there you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Whoa, Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
Okay.
today,
Yeah.
I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda,
Yeah.
and you pressurize this container, and,
Okay.
and the water shoots out that way. So the car goes this way.
Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your
Okay.
stuff. This
Okay.
is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole and weld them on. I don't know if that's...
Something tells me this wouldn't work. So
Okay,
we need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So we'll reuse it. Yeah?
Okay, you know what I'm thinking now, though? I know this... The problem is, I think this is like an oil drum, right?
It is. It's an oil tank from a house.
And these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower or something like that.
So all we need to do is get a pressurized water tank.
Okay.
Put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All right.
Let's get to it, man. Okay.
I got some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me. So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we go.
So I've joined Anthony, and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Ha-ha! So, water car, maxed out version,
Huge.
water tank.
And filled with lots of water and lots of air. Too. Yeah, pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it, okay.
Okay, here we go. 3,
2,
1,
go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That was amazing.
So pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So,
Because then it would be too heavy, right?
Exactly,
Much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water,
Okay.
and then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water,
right?
and I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah.
All right.
Amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out. The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of? Power washer pumpkin carving! The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home. Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did someone say Overwhelmo?
No, wait, no, next. No, not that. Okay, good, okay.
Behold, it is I, Overwhelmo!
Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes?
Is that it?
Yes?
Well, it's not magic.
It is defying gravity.
Nope,
The water would fall and the card would fall to the floor.
it's not magic.
This is magic.
No, it's science.
Horse feathers.
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Balderdash.
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes.
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the. No, that's not my music. Hold. You will rue the day when. That's not my new. Hold. Overwhelmo shall return.
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride. Water car! So
Amazing!
This is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump, that's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump, and we're ready to go. So we fire up the pump, and the water stream comes out really strong. So strong, I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah.
Nothing happened.
No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it, and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way. That's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it down
At the, yeah, exactly.
like that.
And then.
At the paddle wheel, and then the paddle wheel spins, and that propels the car,
Exactly.
right?
Right.
Okay, well, we can do that. Let's do it.
Sounds good,
Put
yeah.
it together. You know what? I have a paddle wheel because I had a failed hydroelectric. This is called flyboarding. Wow. Powerful jets of water are being shot out from this board at my feet. Whoa. The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well, we don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform. Woo-hoo! Flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it. It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo! Our maxed out water car didn't work so well. The main reason is that that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go. Okay, so here's the latest version of the water car, water wheel!
Yeah.
All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan. Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it. And Phil, yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to move
Even
on its own.
half full, you
Even
can't
half full,
move
I
it.
think we need less fuel. We're gonna get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never
Okay.
It never moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go in its own.
Exactly.
Okay.
Wanna get it
Yeah.
down?
Absolutely. Let's do it. We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference.
Yeah,
The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going!
All right!
Amazing! Yeah! Look at it, man, this thing worked like a beauty!
It worked all, it went all the way.
Yeah!
Way to go. The water car, finally a success. It was the push.
It was the push, that's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely!
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.
Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max Experiments at Large. Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the Dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxodrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator.
crushing the competition. It's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the, regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training and we're gonna use the science behind the small balloon-powered car and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law.
no, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later. We're not
opposite
doing
reaction.
this bit now. We're doing that bit in a minute, so we could. No, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
I did.
You did let it go.
I had to let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tanks, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity, he gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart. This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's Well, it's really easier to see if I'm not standing on the ground. Oh, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third.
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right.
Good.
So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked.
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
More tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. Okay. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use 2 balls. I swing 2 balls up, and 2 balls go out that side. Isn't that cool? Now, it wouldn't be science max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and ha-ha! Yeah, it works the same. Okay, now let's try it with 2 balls. Okay, ready? Wait. And 2 balls, throw them out. And 2 balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh. Ah!
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do 2 things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube,
Yeah.
and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go
Or it goes
that
forward.
way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Yeah! Woo! Uh-oh, uh-oh, uh-oh. Uh-oh. Woo-hoo-hoo. That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah, 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 yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.
Science Max!
Put on your helmets for this episode of Science Max. We try to build a human-sized cart powered by inertia, plus Newton's laws from a caveman to crockery. Inertia on Science Max Experiments at Large.
Greetings, race fans and Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the drag racer. Huh? Pretty cool. It works like this. You pull the string and get the wheels going really fast, and then you let it go, and it just drives away on its own. The interesting thing is that I don't have to push it, it goes by itself. It all has to do with Newton's first law of motion, which is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Yeah. Let's get building. Here is everything you need to build your very own dragster. You need some popsicle sticks, some straws, and some shish kebab skewers. I love these. You can get these at the grocery store. Let's see, some elastics, and of course you want wheels, and I just cut my wheels out of cardboard.
So here's a quick explanation of how to build your dragster. First, use anything round to trace 3 circles out on your piece of cardboard. Remember, you want 2 big and 1 small circle. Then, cut out your wheels. Then it's time to make the frame of the dragster using popsicle sticks and elastics. Just put 2 popsicle sticks together, then wrap the elastic band around them to keep them together. First you build one side, then the other side. Then, add some pieces across the middle to give it support. Remember not to put any popsicle sticks too near the ends because they'll get in the way of your wheels. Next, cut the straws into small pieces and use an elastic band to tie them to the ends of the popsicle sticks. Then it's just a matter of sticking the shish kebab skewer in a wheel, passing it through the straws, and sticking on the other wheel. Don't forget that the small wheel goes in the middle at the front. You can trim the skewers afterward by just breaking it off short.
If you want step-by-step directions on exactly how to do this, you can go to our website. It's all right there. Now the last part is wrap some string around the back axle so you can pull and the wheels will spin. Let's check it out and see how it works. Didn't work that well, did it? That's because we haven't added the secret ingredient. Plasticine, the perfect secret ingredient for all of your dragster needs. And also sculpting, because that's what it's for. Remember how I said an object at rest tends to stay at rest and an object in motion tends to stay in motion? Well, the heavier something is, the more force you need to change its direction, either get it moving or make it stop. That is called inertia.
It's the tendency for an object to resist a change in motion, either getting it going or making it stop. So, the heavier we make the wheels of our dragster, the more they will resist a change in motion. So what I've done is I've stretched out my plasticine, and then you roll the wheels of the dragster around in the plasticine, and this will make each wheel way heavier than just the cardboard by itself. And it will make it much better in terms of keeping the dragster going, because if the wheel has more weight, it will have more inertia. Now, I have to wrap the string around the back axle, just like that, and there we go. All right, let's try it out. All right, let's give it a shot and see how it works. Pull on the string, get the wheels going real fast, and there it goes. Now, of course, this is Science Max Experiments at Large, and we are going to do it again, and we're going to do it much, much bigger. That's why I'm going to the Center for Skills Development and Training. I thought it was bigger. Oh, right. Hey, Chris.
Hey, Phil.
How you doing? Chris is from Logix Academy, and he is going to help me max out our dragster. Now, you guys at Logix Academy go into schools and build all kinds of cool stuff with the students, right?
That's absolutely right. This is our dragster over here, actually. And this one has an electric motor, which is kind of fun. And these gears touch.
Ooh.
Wheels get going.
I like that.
And...
Oh, all right. See, our dragster works on good old human power. You pull the string, and there it goes. Now, you have a physics degree, right?
I do.
Which means you know Newton's first law of motion.
Of course, an object at rest tends to stay at rest.
And an object in motion tends to stay in motion. I thought it was gonna come from over there. Yeah, come on. All right, Chris, I want to make a dragster big enough that we can ride.
Whoa, okay. Well, it's gonna have to be pretty big.
Yeah, I think we have enough wood, though, right?
Yeah,
And
looks like
oh, look, I've got some wheels.
perfect.
These are bike tires, and I filled them full of air, so they're bouncy. Check
Excellent.
it out. Whoa, it's okay.
So, yeah, we build our frame out of wood,
Yeah,
attach the tires on, and then find a way to get them spinning.
and if the tires are spinning,
Yeah.
we don't actually have to push the cart because it'll just go on its own?
That's the idea. The inertia should carry, in the wheels, should carry us down the track.
So in this case, the object in motion is the wheels.
That's right.
And it wants to stay in motion, which means that when it hits the ground, it'll push the cart.
And hopefully us too.
And hopefully us too. All right, let's get building.
Let's do it.
So Chris and I get to work building the dragster. Our maxed out version is gonna look just like the popsicle stick version. A triangular frame with 2 large wheels at the back and a small one at the front. What's more, we're gonna do the same thing to get the wheels spinning. We're gonna attach a rope and give it a pull. When we drop it down, the inertia of the wheels should make the dragster take off.
All right, here we have our dragster. This is nice, Chris.
Yeah, it looks good.
So the only thing I don't understand is what are these for?
Right, so these are gonna help us lift the wheels off the ground, like this.
Oh, okay.
Pull it back, and what's gonna happen is we're gonna run real fast with that string, and we're gonna give it a little kick, and hopefully it'll take off.
Ah, all right, I like it. So I just run backwards as fast as I can.
Fast as you can.
All right, here we go. Ready?
Yep, ready?
Okay, safety glasses on. And, oh, wait, did you want to sit on it, or?
Oh, right. Let's wait until we see it working, and then we can...
Okay, dry run.
Okay, try one.
Ready?
Go! Run, Phil.
And go! Yeah!
So here's what happened. Remember, the cart has no power of its own. It was able to drive away from a stop using the inertia it got from its spinning wheels, and a little bit from Chris's kick.
That worked pretty well.
That was awesome.
Yeah.
I think we can make it go even better.
You think so?
I just think we need a bit more speed.
Yeah. All right, well, let's pull it back to the start.
Okay.
So what, the wheels weren't going fast enough?
Yeah, I think so. I think that you running, was great, but maybe if we use something motorized.
Well, I think using a motor feels like cheating.
No, not on the wheels. Maybe,
Oh, just to get the wheels spinning fast?
Yes, that's right.
But I don't know how that would work.
Well, I was thinking a power drill.
A power drill.
Yeah.
I don't get it.
Okay.
How do we use a drill?
Let me explain. So we'll take a drill.
Right.
And we'll attach it right under this axle here. And that'll get the wheel spinning a lot faster than we had it before.
Oh, I see. So you put the drill right here at the end, and it'll spin the wheel.
That's right.
Huh.
That's the idea anyway. And once we get it up to speed, hopefully a lot faster than before, give it a kick, it should go a lot farther.
Okay, great. So that's way better than me running all the way back with the rope.
I think so.
All right. Now here's the real question. Should we just go for it and have someone ride it when we do it with the drill?
Well, who gets to ride it?
Oh, rock, paper, scissors. Okay.
Let's go.
1, 2, 3. Oh,
Yes.
All right. I will get a drill.
Okay.
What kind of bit do we need?
Hex bit.
Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you.
Our dragster worked pretty well, but now we're gonna try sitting on it and seeing if the inertia of the wheels is enough to accelerate the dragster and the human rider. Because we're gonna need a lot more inertia, we're gonna make the wheels spin even faster using a drill.
All right, power tools! Yeah, power tools! Woo! Yeah! Sorry.
When I attach the drill to the wheel, it works really well.
Yeah, that is really gonna work. All right, let's do it for real. So, what do you want? Helmet or blast shield?
Blast shield.
Blast shield. All right, there you go. You ready?
Go. There you go. Whoa, man.
Okay.
Remember, the faster the wheels are spinning, the more inertia they will have.
Ready? Ready. And... Well,
What happened?
so you went a foot. 1 foot. So why didn't that work nearly as well as the last time we did it?
Well, I think my extra weight caused a bit of the problem.
Yeah.
So the inertia wasn't able to carry us forward.
But the whole point of this is so that someone can ride the dragster, because why build it if we can't ride it?
That's exactly right. I think if we're gonna have someone ride it, we need heavier wheels.
Well, on the small one we use plasticine.
Yeah.
I don't know if that's what we should use.
What if we used car tires?
Car tires. Oh, what, on this?
No, I think we're gonna have to build something bigger.
So okay, so we build a whole new frame.
Yep.
What if we got like the axle of, like the back axle of a car or something?
It's a great
The
idea.
back axle of a car, and then what, we use the drill?
I don't think the drill's gonna be enough.
To move the, why? You don't think it's gonna be enough to move the back axle of a car?
Yeah, it's too big.
So what do we do?
Well, what's good at moving the back axle of a car?
Well, I mean a car, but we would have to take it off the car, so.
We could use another car.
We could use another, we could use another car.
You could use another car.
You'll have to explain how that works.
Okay.
Let's go get the stuff, and you can tell me how we're gonna use. So how do we use another car to make the first car go?
Okay, I'm thinking we jack one car up,
Yeah.
back our big dragster.
Newton's laws in 60 seconds.
Isaac Newton was a super genius, and among the many things he did was come up with 3 laws of motion that describe how everything moves or doesn't move. I will demonstrate using myself.
Newton's first law, an object at rest tends to stay at rest. An object in motion tends to stay in motion. Newton's third law is for every action, there is an equal and opposite reaction. Ugh. These sandbags weigh as much as I do. So when I push them forward, I go backward the same distance. Now, Newton's second law is F equals ma. Force equals mass times acceleration. How hard you push something is equal to its mass or its weight times its acceleration or how much you change its speed. I know, that one's a little bit more complicated, so we're gonna have a whole other segment describing that one coming up. Meantime, let's recap. Newton's first law, object at rest tends to stay at rest, object in motion tends to stay in motion. Newton's third law, for every action there's an equal and opposite reaction. Newton's second, Newton's three laws of motion. Now how do I get down? How do I get, oh wait, I know. Oh no, that was not a good idea. That was...
Now it's time for Science So Simple, a caveman could do it. This is a caveman. This is a door. It is a well-known scientific fact that cavemen do not know how to open doors. This is Newton's second law. Force equals mass times acceleration. Our caveman thinks he can open the door if he uses force. Well, what if he was to walk briskly into the door? Then the force that he will hit the door with will be equal to his mass, or how much he weighs, times his acceleration, which will be walking speed to 0. It didn't work, did it? No. Looks like we need more force. If we want to increase the force, we need to increase the mass, increase the acceleration, or both. A rock! That's perfect. If the caveman holds the rock, he has a greater mass. Now we just need to increase the acceleration, which means going faster. Let's try running. Go on. A little further. That's good. Now the caveman is going to run at the door. To get more force, we've increased the mass to a caveman plus a rock. And we've increased the acceleration to go from running speed to 0. And there you have it. That's how Newton's second law works. Join us next time for how doorknobs work.
What?
Our inertia-powered dragster just wasn't maxed out enough. So Chris and I built a second dragster, the Dragster Mark II. This one is a welded metal frame, and instead of bike tires, we're using car tires because they're much heavier than bike tires. And to get the tires spinning fast enough, we're going to use a car. That's right. We jack up an actual car and have the tires touch each other. Then we can get those heavy tires spinning fast enough to get enough inertia to get me going from nothing. The Science Max build team pulled out all the stops on this one. Just like the smaller version, the dragster has to be up on jacks so the wheels don't touch the ground as they get spun up. The wheels of the dragster touch the wheels of this working car, which is also jacked up. That's how we're gonna get them spinning fast enough.
Chris is over there. He's got a rope, just like I'm gonna have a rope. And when we're ready, we're going to run forward and pull it off the jacks, and our dragster will go. We hope, right? That's the plan, right? Yep. All right.
I think it's gonna work.
I think we should do it. Ready, Chris?
Ready.
You ready, Paul? Ready. Fire it up. Go, go, go. Faster, faster, faster.
Keep
Faster,
going.
faster.
Keep going.
All right, Chris. After 3, right? 1, 2, 3, go. Nice. It's pretty good. Yeah, that worked. All right, are we ready for me to be in it?
I think so.
All right, we're gonna do it. The helmet's in the Max van. Do you have the keys for the Max van? Keys for the Max van. Here's another small experiment you can do with inertia. Take a stack of checkers or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now you can knock checkers out of the middle of the stack without the stack falling over, if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it. Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of...
Well, our inertia-powered dragster worked really well. And now it's time for the final step. Me, riding it to glory!
Now, I know it probably doesn't need saying, but don't try this at home. Not that I think you really can try this at home because this is kind of involved, but I figured I should probably tell you guys just in case you were tempted to try it at home. We know what we're doing. We know what we're doing, right, Chris?
Yes.
Yes, we know what we're doing. All right.
Fire it up. Keep it going. Keep it going. All the way. Whoa. All the way. 3, 2, 1, go! Woo!
Yeah! Yeah!
Woo! How's that for inertia?
Wow, look at that. That's amazing.
Cool.
High fives! Yeah!
Let's recap. The weight of the tires, as well as how fast they were going, provided enough inertia to accelerate me and the weight of the dragster. The objects in motion, the wheels, wanted to stay in motion so much they moved the dragster all by themselves. Inertia, and Newton's first law of motion.
Thank you for joining us on Science Max. Let's go again. Your turn?
Yeah, my turn.
Okay. Woo.
This episode of Science Max is all about storing energy and releasing it.
Yeah. Let's try it out for real.
Storing it in a giant spool racer, plus a domino chain reaction, mousetrap chain reaction, popsicle stick chain reaction, and more. All on this episode of Science Max Experiments at Large.
Okay, 3, 2, 1, go.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. Wow, I really need some more energy. Fortunately, I have some saved up. Ah, that's better. Yeah, I know what you're thinking. Storing energy like that doesn't make a whole lot of sense, but you can store energy, and that's what this episode of Science Max Experiments at Large is all about. In fact, I'm gonna store some energy in this container simply by putting it up here on the top shelf. More on that later. But right now, let's look at another way that you can store energy and release it in a really fun way. We're gonna make a spool racer, and it's pretty simple. Here's all you need. You need some science ribbon. Now, if you don't have science ribbon, you can use regular ribbon, but the ribbon really isn't important. It's the spool that's important.
You'll also need a washer, elastics, pencil or pencil crayon, popsicle or craft stick, and science tape.
Science tape is the same as invisible tape, except I use this one only for science. Here's how you build it.
Break the popsicle stick so it's smaller than the diameter of the spool. Then put the elastics on top of the pencil and pull them tight, thread the popsicle stick through, and feed it all through the hole of the spool. Grab the elastics on the other side and pull out the pencil, and everything will be threaded perfectly. Then stick on the washer and thread the pencil through. Finally, tape the popsicle stick down so it doesn't move. And if any of these steps are a little too fast, don't worry. All of the instructions are up on the website. That was cool. I can't make it go away. I can only make it come up. So there you go, a spool racer. And here's how it works. You spin the pencil around, and that twists the elastic. Now that elastic is gonna wanna unwind, right? So just keep spinning that pencil around until it's good and tight. And then when you put it on the ground, the pencil's gonna wanna unwind, but it can't because the table's in the way now, which means that the energy is gonna transfer to the spool, which is gonna turn, whoa, and it's gonna drive away. Yeah, let's try it out for real.
So why does this work? It works because the elastic is coiled, right? Yes, and because I'm putting in the energy to twist it. You see, I'm putting in effort to spin this pencil crayon around, and then when I've finished, all of my effort has been stored in the elastic. When I let it go, my energy transfers
Into movement. So that's, that's what we're gonna do today, Science Maximites. We're gonna max out the spool racer. I think Anthony would really know how to help me with this. So, I'm off to the Ontario Science Center. Come on. What happened?
You okay?
Anthony.
Yeah, hi.
Oh, were you in the middle of something?
Don't worry about it, yeah.
Oh, okay. Sorry about that. You know what, I was wondering if I could get your help with something.
Sure, yeah.
Yeah, one word. Spool racer. Actually, that's two words. Spool racer. Yeah. You want to help me max out a giant spool racer?
Yeah.
Awesome. Let's go back to Science Matt's headquarters. Okay, Anthony. Today I want to max out the spool racer.
Awesome.
Right? So you twist up the elastic and it goes from potential energy, all stored, to
Kinetic
energy. Whoa, there we go.
That's awesome.
So,
okay.
Not too hard to design. Should be fairly easy to max out.
Yeah, really simple couple of parts here. We just got elastic band inside.
Yep.
And then this big long pencil to store the energy and then release it.
And the most important part
is spool.
Is the spool.
Exactly.
And I know where we should start.
Where's that?
Right here. This is an industrial cable spool. So the big, thick electrical cables, they come wound on this thing.
Yeah, okay.
So I figure we start with this.
Got it.
And the good news is that it's got a hole already. And check it out, it rolls really well, right? Okay, cool.
Okay.
So, bungee cord?
Yep.
And long pole or something?
Yeah.
And we're ready to go.
I guess let's get some parts.
Okay.
Okay.
Oh, hey, how you doing? You want to buy something? I got a lot of stuff here, and I got a special today only. Potential energy, huh? I will throw in some potential energy with any order. You see this stuff on the shelves here? The stuff on the higher shelves has more potential energy than the stuff on the lower shelves. Don't believe me? Here, hold on. Look at this state-of-the-art traffic controller. Right now, it's sitting up here on this high shelf. Now, if it were to fall, it would be going fast, which means it would have a lot of kinetic energy. You see, when it fell down, it had enough kinetic energy to completely break itself apart. Yeah, well, that's the difference between potential energy and kinetic energy. Look at this bagel, just sitting here, not moving, minding its own business on top of this ramp. It's all potential energy and no kinetic energy. And when it gets to the floor, it's all kinetic energy and no potential energy. And now it has neither because it's on the floor and it's not moving. 5-second rule. And now you know your energy. So what do you say? You want this thing? Tell you what, I'll give you a discount because you know it's gently used. Hey, I'll even throw in this bagel, huh? Also gently used.
Anthony and I are maxing out the spool racer. We start with a long coil of bungee cord, which is kind of like a giant elastic, and feed it through the spool. Then we put on a big piece of plastic to act as our washer and use a long pole as the pencil. We flip the spool on its side to wind it up. Then we flip it back and it's ready to go.
All right, so we have it all wound up and we're ready to try it again, but with one change.
Phil,
Yeah,
what's with the trike?
I ride the trike.
It's like I always say, what's the point of building something big if I can't ride it?
There's no way you're gonna fit on this thing.
No, I don't put my feet on the pedals. I put my feet here on the back, right? And then-
Okay, yeah, I get it. You got it?
Hold on, I gotta do my helmet up.
Safety first. You ready?
I'm on it.
Okay, 3, 2, 1, go.
Oh, it's working.
It's working. Amazing.
All the stored energy in the bungee cord is being released and the spool starts to turn. There's even enough energy that I can get pulled along behind it.
It's not going that fast, though.
No, and
It's pretty good, though. It still pulls me.
right? Yeah, pretty good.
So, Spool Racer, actually able to get pulled by it.
Yeah.
You know what? I think we can go even bigger.
Bigger.
Yes.
Well, what did you have in mind?
I'm glad you asked. Yeah!
What is this?
This is an industrial cable spool, and this is the biggest size that they make. And I thought we would do the same thing with this. What do you think?
I think this could generate a huge amount of energy.
Okay, so all we gotta do is just build it just like we built that other one.
Just bigger.
Except way bigger. Let's do it. When you set a domino on its end, you're giving it potential energy because it can fall. Ooh, and when you put two dominoes together, you can start a chain reaction because that one will fall into that one. Ah, but it's a lot more fun with more dominoes.
Setting up a run of dominoes is a lot of fun, but it takes a flat surface and a steady hand. And if you want to do it yourself, add gaps, so if one part falls, it doesn't take out the whole run.
Last one. There. I had some dominoes left, but I did it. I made the Science Max logo. See?
Science
right?
Max!
Sort of. Let's see how it works. Ready? Yeah! Now it's time to max it out. Giant maxed out dominoes! Woohoo! Even though these dominoes are giant, they're still gonna work the same. They're standing up on their ends, which means they've got some potential energy. And when I give this one a push, that potential is gonna turn into kinetic energy, and it's gonna knock the next one, and the next one, and the next one. I hope. I don't know what's gonna happen, but let's find out. You ready? Okay, 3, 2, 1. Giant dominoes! Yeah, science! The problem is, when you use dominoes this big, setting them up again is a real chore. This is a mousetrap, but don't worry, no mice are gonna be harmed in the making of this episode. Mousetraps are a great example of stored energy. You see, in order to set a mousetrap, you have to push this bar back, and it's hard to do because the spring holds it. And then you set the mousetrap by putting this little lever underneath this very sensitive trigger, and once you have it set, all that energy is stored as potential energy, but it'll go off with just the slightest touch, releasing the energy. So what if I had a number of mousetraps and they're all set and all of that potential energy is stored up, and I dropped a number of ping pong balls on them? Well, then I could set off a chain reaction where one mousetrap flies and hits another mousetrap that hits a ping pong ball, and then they all go. Now, this is something you can try at home, but do not set the mousetraps yourself. It can really hurt if it snaps on your fingers, so you should probably ask an adult to help you, and then you can see how brave the adults in your house are. Okay, you ready? Here we go. Mousetrap chain reaction. And last one. There we go. And now,
Let's max this out. Let's do it with 90 mouse traps. And this is a crate of ping pong balls. So let's see what happens when we put them together. There you go. Maxed out ping pong ball, mousetrap, chain reaction. Awesome.
Ready?
I'm on it. Anthony and I have built a large spool racer.
Oh, it's working. It's working.
And it worked so well, the only option was to go bigger.
What is this?
This is an industrial cable spool, and this is the biggest size that they make.
I think this could generate a huge amount of energy.
Building our giant spool racer is the same process as the other builds.
So the steps are exactly the same, but on a larger scale. And this time we're gonna use, obviously, the large spool, and we're gonna use this 2x4 as our pencil windy thing.
Coil some bungee cord, feed it through.
Ready?
Yep.
Okay, here it comes.
There we go.
Got it?
Haha, yeah. Add a washer and a long 2x4 to act as our pencil.
And now we stick the giant 2x4 inside the coil.
Just about. Yeah, we got it.
There
okay,
we
cool.
go.
And we're ready to try it out.
So it looks like we're ready to go.
Yeah, exactly.
Do you want to do it in here or you want to do it outside?
Oh, definitely outside.
Okay, let's go.
Yeah, okay, cool.
Yep. Oh, it's heavy. Batteries are great at storing energy. They store electricity.
Batteries?
But if you're like me and you have a whole bunch of batteries and you don't remember which are the good ones and which are the dead ones, there's a trick that you can use to find out. Get a frying pan or a brick or concrete floor or something else that's very, very hard and an adult's permission. Here's the secret. Dead batteries will bounce and batteries that still have some life in them won't. Watch. Good battery. Dead battery. Now, it's a little hard to see, but listen. 1 hit, 2 hits. Here's what's going on. See, batteries store electricity in the form of a gel, sort of like modeling clay. This is modeling clay, fresh from the fields, where the pits, the mine, wherever modeling clay comes from. And this is modeling clay I've left out for about 5 days, so it's all dried up and hard. Now, when modeling clay is new, it's all wet and soft, and when you drop it, it doesn't bounce very well. I've left this piece of modeling clay out to dry for about 5 days. Now it's all dried up and old, and it bounces. New, old. So, same thing with the battery. Good batteries won't bounce, and bad batteries will. Science. Here's a fun chain reaction you can do with popsicle sticks, or craft sticks, because these ones are a little bit wider than popsicle sticks. It is because these kind of sticks are slightly bendy, and when you bend them and put them together in a pattern in a certain way, you can keep them under tension, and then they want to snap back, and then they'll fly. So here's how you make the pattern. Ready? You take a popsicle stick or a craft stick, and you put it down on the table. I know, okay, it's a slow start. Then we take another one and put it across. Now comes the secret. The secret is over and then under. You want to put it over one and then under another, like that. And then this one, over, under. Put it over the one that looks like it's the top stick and under the stick that looks like it's the bottom stick. And then it starts to hold tension. It starts to hold the potential energy.
Continue this pattern. Each stick goes over and under the 2 sticks at the end.
Now here's the trick. Soon as this one lets go, then that one will let go, then that one, then that one, then that one, and that's how you get the chain reaction. They all start flying up. So you have to build it with never letting go of that last stick. You gotta always remember to keep a hand on it, or else you'll have to start again. So, okay, so you ready? You wanna see me let it go? Here we go. I know, that isn't so great because it's better if it's a longer chain. So fortunately, I have a longer chain. I've got a binder clip on this end, keeping the craft sticks together. Ready? 3, 2, 1. Wow! Release of kinetic energy from the potential energy of winding all the craft sticks together. Fun, and you can totally do it at home. Now, let's max it out. Behold, almost 800 craft sticks in a long, nicely designed triangle. Ready? 2, 1. Yeah! Craft stick chain reaction. I'm gonna go get something to clean this all up with.
All right. So Anthony and I have built a giant spool racer and have taken it outside to try it out. In order to wind it up, we flipped over the last version on its side. But this spool weighs 200 kilograms. Easy to roll, almost impossible to flip over.
Come on, get it.
I don't think it's gonna work. It's too heavy to move.
Yeah.
We should have thought of that before.
Well, I'm sure we'll think of something.
So Anthony and I thought about it. And thought about it. And thought about it.
I got it!
What?
No.
But you...
And the answer finally dawned.
What if we roll it this way? Because then that would wind it up, right?
That's brilliant!
By rolling it backwards, we wind up the bungee cord in one direction, which will make it want to unwind in the other direction. Anthony and I roll it across the parking lot to get it wound up tight.
I don't think I can hold it anymore.
Okay. Okay. Let go. Okay, it's wedged.
It worked.
All right, one more thing. We're gonna hook the trike up to this one as well.
Okay.
Okay. So right now, it's all wound up, and when it gets moving, the potential energy in the coil will turn into kinetic.
Exactly.
Kinetic energy. Now, just in case you're tempted to try this at home, I need to tell you, do not try this at home. We're trained professionals, right?
Yes.
Yes. Well, as much as anybody can be trained for this, because no one really does this.
Are you ready?
Ready?
Okay, here we go.
Whoa. It's working!
It's working!
Yeah!
Sure enough, all the potential energy we stored in the bungee cords starts to unwind, which rolls the spool and pulls me along behind it. What's more, that big heavy spool has a lot of momentum. So when it gets going fast, it just wants to keep moving. It wasn't long before I had to jump off.
Uh-oh.
That was amazing!
All right, that had a lot of kinetic energy.
That was a ton of kinetic energy.
There you go, Science Max, experiments at large, massive spool racer. Your turn next?
Yeah?
Okay.